Hello, everyone. Welcome to pre-lecture 22. This is going to be covering Introduction to the Laws of Thermodynamics. And again, we'll be in chapter 16 here. Okay. So where we left off last class was talking about what entropy is, in particular how we quantify it using Boltzmann's equation. Reminder that we abbreviate or represent entropy rather with the variable S. We have the Boltzmann constant shown there, and then W is the number of microstates. And as the equation would suggest, the entropy of our system will increase as the number of microstates also increases. And so one of the things we want to know how to do then is calculate the number of microstates within a system. And so let's start with a simple example. Suppose we had a box with 8 spots in which 4 different particles can be arranged. And how would we go about essentially figuring that out? So on the slide here, I've drawn a couple of boxes. Say we have 4 particles. One arrangement that we could do, if this is a particle, this is a particle, this is a particle, this is a particle. Great, we've done that. That's one arrangement. Another arrangement we could do is maybe alternating up and down. That's another arrangement, right? And we could fill all of these in. If I clear these, of course, we could also arrange them like this, where all 4 are this way, or maybe we have 3 on one side and 1 all over by itself. All of these are valid and probably equally as likely microstates. And so how do we actually calculate that number? We do it probabilistically. And so W, if all of our particles are going to be different, which in this case our question would tell us that there are 4 different particles, so these are not the same, we would essentially say when we put our first particle in, we can put it in any of 8 spots. After that, one of those spots is taken, so we only have 7 spots to put it in, and 6, and then 5. And so if we are to then figure out what our number of microstates is, we just solve this, where we do 8 times 7 times 6 times 5. And so when we do that, I got a value of 1,680 microstates. And so that is how we would calculate the number of microstates. Obviously, in pretty much any chemical system, we don't have 8 spots. We have billions, if not trillions, if not more than that. So microstates get to be quite numerous, and we'll go through more in class how to figure those out for larger systems. Yeah. However, I want to take the rest of the pre-lecture video to kind of go through our laws of thermodynamics. And so what these are is a series of empirically derived, and what the phrase empirically derived means is from experiments. So people performed experiments, derived these observations relating temperature, energy, entropy, heat, and work all together. And so these form our laws of thermodynamics. And weirdly, we don't start with the first law, we actually start with a 0th law of thermodynamics. What that states is that if 2 bodies, which is not, of course, like human bodies, but any 2 things are in thermal equilibrium, then a 3rd body would also be in thermal equilibrium. So essentially, things that are the same temperature will also be the same temperature as something else, right? Sounds pretty basic, but it is important for understanding thermodynamics as a whole. First law is essentially our conservation of energy. So that is stating that in a closed system, the difference between any heat supplied and work done by the system on the surroundings must be equal to internal energy. We're not going to cover the first law all that much in Gen Chem 2 here. If you end up taking more chemistry, you'll cover that a lot more. So I want you to know what the first law is, but you don't have to remember it for a quiz. Second law is very important. We'll talk a lot about the second law of thermodynamics in our class. It states that all spontaneous changes cause an increase in the entropy of the universe. And so we'll dissect that more in class, as well as even next week. expect what our phase integration is going to be about as well. And lastly, we have the third law of thermodynamics, and that states that the entropy of a perfect crystal at absolute zero, so 0 degrees Kelvin, is 0. And that is actually where we will finish off this lecture. And so this course, just to reiterate, the second and third laws are really what we're going to focus on. If you take more chemistry, you'll get back into the zeroth and first laws, but for our class, it's mainly on the second and third law. Okay, so let's talk a little bit more about the third law of thermodynamics. It states that the entropy of a perfect crystal at absolute zero is 0 as well. And so we can represent this using the Boltzmann equation here. It essentially says that when we are at 0 degrees Kelvin, there is no molecular motion. Our temperature is absolute 0, right? So we don't have any translation. That means any movement of molecules along an XYZ axis. We don't have any molecules rotating or vibrating. And so there's only one possible microstate. We take, of course, log of 1, we get 0. And so our entropy in that system would be 0. Okay. And that is essentially what I just said there. And so something you could try here is calculating the entropy of a 3-atom, 6-location universe in which all 3 atoms are different. And I would recommend doing this right now. We'll also go through this one in class. But just to hammer home the importance of the third law, it is that we can set an absolute value for entropy at absolute 0. That is the importance of the third law. It sets us not just up with differences in entropy, but an absolute value. Okay. So within that, because we can have an absolute 0, we can also derive and determine absolute entropy values under specific conditions. And so this is a property we call standard entropies. And what that means is that all of these are for 1 mole of substance under standard conditions, which is 1 bar of pressure at 298.15 Kelvin or 25 degrees Celsius. The standard entropy change can also be calculated. And so I've defined all the terms here where delta S standard is equal to the sum of the number of moles of standard entropy values for the product subtracted by the sum of the number of moles for entropy of reactants. Okay. These values are found in your textbook, back of your textbook. I'll reference them a couple times in class, and you may need them to solve an equation or two. Okay. That's it for the pre-lecture video for today. If you have any questions, please let me know. Otherwise, we'll talk more about it in class. Have a good day.